Welcome back. Like I promised you on this part of the lecture, we will see how we can use the concept of concentration to do calculations. And we're going to use two of them basically, the mass percentage as a measurement of concentration of a solution and the molarity. So let's begin with the mass percentage. A mass percentage is nothing more of what I just said. It's the percent of mass of the solute over the solution. So it's going to be the mass of the solute, which is what we are dissolving, divided by the mass of the solution. And since we're talking about a percentage, multiply by 100. More specifically, and which is the part that we really need to understand, is going to be the mass of the solute divided by the mass of the solution, but the mass of the solution is nothing more than the mixture, right? Which is nothing more than the mass of the solute once more, combined with the mass of the solvent, what you're using to dissolve. All of these multiplied by 100. And this is what we call the mass percentage. So most of the concentrations, with the exception of molarity, which we are going to discuss later, most of the concentrations are going to be solute over solution. On this particular one is the mass of the solute over the total mass of the solution, which is the solute plus the solvent. So let's do some problems here to see how we can apply that. So let's do the first one. Calculate the concentration of each solution in mass percentage. So 178 milligram, that's definitely smaller than 4.91 grams. And the one on the bigger proportion is always the solvent. So the C6H12O6 is our solute. The water is our solvent. And the solution is the solute plus the solvent. And you already know that. I'm just kind of reviewing as we go. So to do the percent mass, you can also write it like this. That's going to be the mass of the solute, which is 0.178 grams. Notice that I took the milligrams and I converted into grams because percentage do not have units, so the unit had to cancel. Therefore, the units have to be the same. And the solution is going to be the solute combined with the solvent. So when we do that, we are going to have, give me a second to pull out my calculator, please. When we do that, we're going to have 0.178 grams over 5.088 grams. And we are going to multiply this by 100 to make it a percentage. And that's going to be 3.50% mass. So this is a solution that is not that concentrated, right? It's going to be just about less than 4% concentration of the C6H12O6. Let's do the second one. So once more, the majority of the concentrations are going to be solute over solution, not over sorbent. And the mass percentage is nothing more than the mass of the solute over the mass of the solution, which is the solute plus the sorbent. So on the next one, we're going to have 7.55 grams of NaCl, and this should have been water, over the solute, which is what we have on top, plus the water, which is 155 grams. And we're going to multiply that by 100, so the percentage is going to be 7.55 grams divided by 162.55 grams multiplied by 100. That's going to be 7.55 divided by 172.55. That's going to be 4.64%. The grams cancel. So 4.64% is going to be the mass percentage of these solutions. So that's how we find the mass percentage. How do we use it? Well, before we use it, let's go ahead. You can go ahead and practice a little bit. So what would be the mass percentage for this particular soft drink in terms of the sodium? So how we can use this mass percentage? Determine the amount of potassium. So we're looking for amount. So we're either looking for moles or mass, grams or something like that. So potassium chloride, KCl, in this solution. So the solution is a solution that is 1.08% KCl by mass, and we're asking to find out if we had that much solution, if we have a total solution of 19.7 grams, how much of that is potassium chloride, given that is 1.08 potassium chloride per solution. So the first thing I will tell you is that you have to take that percentage and make it into a conversion factor. So you gotta make it look like a fraction, a conversion factor. And since this is a percentage, we always going to say, whenever something is a percentage, we always are going to say that it's over 100. Since we're doing mass percentage, we're gonna say that those are grams. And we know that this particular one is 1.08 grams of KCl for every 100 grams of what? Not the solute, not the solvent, but the solution. So that's how we can translate a mass percentage to a conversion factor. Now that we have a conversion factor, we can solve this problem. We're trying to find the amount in grams of potassium chloride given 19.7 grams of the solution. So it's super important that we label everything that we're using. Since we have a conversion factor, we are looking for the KCl, so we need the grams of KCl, and we care less about the grams of the solution, right? Because we want to be able to cancel that, and that's going to be nothing more than 100 down here and 1.08 there. So we took the percentage. We took the percentage and we converted into a conversion factor. Given that it's a percentage, it's always going to be over 100. You just have to make sure that you know over 100 of what. And that way you can set it up like that. So when we do that, then all we have to do is take 19.7 multiply by 1.08 and divide by 100. And that's going to give us 0.21 grams of KCl. So if I have a total of 19.7 grams of the total solution to be 1.08%, I'm going to have 0.21 grams of KCl. So the most important part here is to be able to recognize that you can take a mass percentage and make it into a conversion factor. And once you have a conversion factor, it's just you should be able by now to do it automated by setting up the train track and eliminating what you don't want. But you gotta be careful. You have to make sure that you label everything. That way you know which grams you're talking about, which one goes on top, which one goes at the bottom. So with that said, go ahead and practice a little bit with this one. And once you're done with that, you can also do, actually this, let me see. This is a learning check. Let me show you another one. So don't practice it. Let me show you another one. A hard water sample contains this percentage of calcium by mass percentage. What mass of water? So on this one, we're looking for the solvent that we have. So how do we do that? Well, we know. Before we do anything, let's take that percentage. So that means it's a percentage. So that means it's gonna be over 100 grams of the solution. And according to this percentage, we have 0.0085 grams of calcium 2 plus, or calcium in the form of the ion. So that would be my percentage. That's my solute over the solution. But the question is asking for the mass of water. And we have a problem because, not really a problem, but we're looking for water. What do we have on our conversion factor? We have calcium and we have solution. There's no water in there. So how do we find that? Well, let's see. Let's do it this way. Let's not find the mass of the water. Let's find the mass of the solution first. So we're gonna find the mass of the solution instead. And from there, hopefully we will find the mass of water. So given that I have 1.2 grams of calcium, I can find, with that information, I can find the grams of solution, because I don't want the grams of calcium, so I'm gonna cancel those. And I know that is 0.0085 for every 100 grams of solution. So let's see what happens when I do that. 1.2 times 100 divided by 0.0085 is gonna equals 14,118 grams. So that's basically over close to 14 liters of a solution, which makes sense if you have such a small percentage, 0.0085. So what does this tell me? Well, my total solution is 14,118 grams, right? But I know that solution contains 1.2 grams of the solute. So given that the solution is nothing more than the solute plus the solvent, and given that I have 14,118 grams of the solution, and I know I have 1.2 grams of the solute, so can I find the grams of the water? And the answer is yes. So if I take 14,000 and take out 1.2 grams, the remaining should be water. So that's gonna be 116.45 and so on. Okay, so with the percentage, with my mass percentage, I was able to find the total mass of the solution. But since the solution is solute plus solvent, and I know how much solute I have, right? 1.2, then the solution minus the solute should give me the solvent, and the solvent is the water, so that's how I find the total amount of water. So you gotta apply the definition of what a solution is. So with that in mind, now you're ready to do that one. And once you do that one, we are done with the mass percentage. So what other concentration we have that is super important up to this point? It's gonna be molarity. And the symbol for molarity is gonna be capital M. And I'm gonna tell you what I tell my students every single semester. The moment you see that capital M, learn to hate it. You do not want the capital M. What you want is what the capital M means, which is moles of solute over liters of solution. The capital M doesn't help you at all. This is a conversion factor that you can use. So if you see capital M, immediately change it to moles of solute over liters of solution. And if you're given a value with capital M, it's going to be 1 liter of solution with as many moles as they tell you. So let me show you. So let's calculate molarity first. So molarity, better known as capital M, which is moles of solute over liters of solution. That's what we do. We take the moles of solute and divide it by the liters of solution. So the molarity of question A is going to be 0.127 moles of sucrose over 0.655 liters. Notice that I was given milliliters, but I know molarity is over liters. So that's what I did. I changed it to liters, and then whatever that gives you. So I'm not going to do that. You can do that on the calculator. What about the next one? The next one is 0.205 moles of potassium nitrate divided by the liters of solution, not solvent, solution, 0.875 liters. So after you do that on your calculator, you're going to have whatever number you got, moles over liters, which is nothing more than molarity. And the last one is going to be 1.1 moles of KCl, or potassium chloride, over 2.7 liters of solution. And that's going to be your molarity, which is going to be whatever number you get, moles over liters. And as simple as that. Just take the moles of the solute divided by the total volume of the solution in liters. And we can use this. Remember I told you, as soon as you see the capital M, what do I need you to do? Hate it, and immediately translate this into 0.85 moles over 1 liter. If you're giving a value with the capital M, always put 1 liter at the bottom. That's a conversion factor. So if I have a problem like this, how many moles of NaCl? So moles of NaCl, that's what I'm looking for, given 0.44 liters of solution. That's nothing more than a train track. You don't want the liters because you're looking for moles. And what did we just put in there? Moles over liter, that's the molarity. And the molarity is 0.85 moles for every 1 liter. Once you have that set up, it's just a matter of multiplying and dividing, right? So you can find the moles if you're given the molarity. Can you find the volume if you're given the molarity? Well, once more, as soon as you see the capital M, get rid of it and translate it. Moles of KCl over 1 liter of solution. Once more, if you're given the capital M, then that means it's per 1 liter of solution. So can I find the volume? Can I find the liters? That's the question. Given 0.50 moles of KCl? And the answer is yes, I have a conversion factor. I do not want the moles of KCl because I want the liters of KCl, right? So 1 liter over 0.255. And once you do that, you can find the volume. So once more, molarity is nothing more than another conversion factor. It's moles over liters. Use it however you want to use it to cancel what you don't want and carry over what you need. So with that said, go ahead and fill up that table. Notice that this table is just a beginning to review for the final. This table you're given grams, so you're going to have to change it to moles first to be able to do molarity. And remember that molarity is nothing more than what? Moles over liters. Moles of solute over liters of solution. So once you do that table, then we have another problem. And the problem is, how can we relate molarity to the concentration of the ions in an ionic compound? So for example, if we have this ionic compound, sodium chloride, and it have a molarity of 0.85 moles per liters, what would be the concentration of Cl? Well, let's put it this way. If I have 1 mole of NaCl, when that breaks into the ions, that's going to be 1 mole of Na plus 1 mole of Cl negative. So the relationship between the ions is 1 to 1, which means if you have 0.85 moles per liters of NaCl, then you're going to have 0.85 moles of Na plus for every 1 liter and 0.85 moles of Cl negative for every 1 liter. So the concentration of the ions, because it's all 1 to 1, is the same as the concentration of the actual compound. So the answer to this will be still the same. What about the next one? The next one, we're looking for the concentration of ammonium given 0.85 moles per every 1 liter of ammonium phosphate. If when this dissolves, this is gonna give us 0.85 moles of NH4 plus for every 1 liter plus 0.85 moles of phosphate for every 1 liter. However, notice that the ammonium is 3 to every 1 PO4. So this is going to be times 3, and this is going to be times 1. So the molarity of the ammonium is going to be 0.85 molar times 3, which is going to be 2.55 molar. So all you have to do is look at the formula, see what is the ratio between the compound and the ions, and then just multiply by that ratio, and that should give you the concentration based on the ions themselves. So once you do that, you should be able to do that problem. And once you're done with that problem, pending more practice on your part in Alex, we understand what molarity is. It's nothing more than a conversion factor. Capital M is moles over liters, moles of solid over liters of solution. And you know how to use it in calculation because it's nothing more than a conversion factor. And you can use dimensional analysis, which we familiarly call the train track method. And you can also do it with the concentration of the ions. When we come back, we're going to continue on this chapter, and we will be talking about dilutions. And you know how to do this, because if you ever prepare a lemonade, for example, and it was too strong, you know that you can make it softer by adding water to it, making the volume bigger by adding more solvent. If it was too soft, then you can make it more concentrate by adding more solute. So we're gonna see how we can predict how much we will need by using a dilution formula. So that's what we're doing when we come back. So I will see you very soon with that information. Take care.